Hi, good afternoon, everyone. Thanks for joining. So we have some participants on Zoom and some participants in person. Please, if you have any questions, post them on the chat and I will read them out here for the in-person folks, and anyone in person, please feel free to interrupt me and ask any questions that you have. This workshop is mainly intended to be if you're a new user of high performance computing. Oh, no voice. Suvrab, could you please check your audio? Okay. So this workshop is essentially intended to be if you have never used high performance computing before and you would like to get started, how would you go about doing so? And the goal really here is by the end of today, you will have access to a cluster. And then day 2, you will actually do some hands-on programming on the cluster and become familiar with the Expanse cluster. So if you haven't had a chance yet, please take this intake, fill out this Google form. It's a short intake form to get to know the demographics and how familiar you are with programming, parallel computing concepts, and high performance computing. So this workshop is jointly organized by Research IT and the San Diego Supercomputing Center. So what this workshop is and isn't. So we will ensure that everyone has access to a HPC cluster and give you a broad overview of high performance computing, not just here at UCSD, but also national resources available in the country. So the third bullet point, national cyber infrastructure landscape, refers to all the different resource providers, and especially through this program called NSF Access, which I will explain through this workshop. And then day 2 is essentially you now have access to a cluster, actually do hands-on training on that HPC cluster. But what this workshop isn't meant to be is a detailed programming workshop. We will provide you with resources that you can follow, like self-directed tutorials and a lot of resources that we can point you to, including interactive videos. But in the workshop, we will not be doing detailed programming or anything of that sort. So let me start with a general guideline of getting started with high performance computing. So first, just trying it out, see if it's necessary for the kind of problems you're trying to solve or the science that you are trying to do. This workshop is mainly to help you get started with that first step of trying out HPC. And then as we move forward, I'll explain the other 4 steps as well. So we'd like to start with learning objectives. So for day 1, it's evaluating the suitability of HPC and the appropriateness of transitioning from, let's say, your laptops or your desktops to these high performance computing clusters. And then trying to understand what resources are available both at UCSD and nationally, and practical exposure to San Diego Supercomputing Center's Expanse cluster. So why HPC? So if you're trying to go from personal computers to clusters, high performance computing is a field that develops computing hardware and the software to solve problems that are beyond the capabilities of traditional computing systems such as desktops or laptops. So there's limited capabilities that I could do with my laptop, and especially when you want to do large scale problems, we need high processing speeds, a lot of memory. Nowadays, AI and ML is quite a hot topic, and if you want to do any of those training, you are more likely to need access to some of these high performance computing clusters. So we did a survey of users in various fields of science, and we covered quite a few different fields of science on the benefit of using HPC. So this slide shows the breakdown of users who, before they moved to HPC, they were working on either their laptop, desktop, or some kind of a custom built workstation. And what we see here is that there's a significant percentage of people whose it took for a single job to run, for a single simulation to run, it can take up to 3 to 5 days. There are few people in the less than 1 hour or 1 to 6 hours, but there's a significant in this 3 to 5 days or 1 to 3 days, 1 day users there. And the intent is to try and bring that time down so that you can effectively do your science quicker. So an open question, participants from the Zoom, please add to chat, or anyone on in person here, please feel free to raise your hand and give an answer. When do you think is it correct to when do you think HPC is the right choice, or moving from a desktop to a HPC is the right choice? Yep.
When you're trying to analyze large volumes of data.
Thank you. Yes, the one of the answers was when you're analyzing a large volume of data. That's absolutely correct. You will need HPC there. Yep. Excellent. Yes. Yes. So laptops might have, maybe some latest ones will have 32 gigabytes of RAM, but that may not be sufficient, in which case you need much larger memory. HPC is right there. Any other answers? Okay, so here's an incomplete list that that I put together. And my personal reason for moving to HPC was I burnt my laptop's RAM. Like, I ran so many cases on my laptop that it actually burnt the RAM and had to replace it. So that's when I moved. I needed a HPC system. So the first one, when you're overburdening your laptop or desktop and it runs very hot, a very common situation. Another very common situation is you have a code which may not take a large amount of memory or processing power, but you want to run this hundreds or thousands of times. For example, you want to do a parameter sweep, right? You want to change different input variables and run the same code again and again. So this is another great case for high throughput computing. This is another place where HPC would be great for your application. So I won't go through all of them, but it's quite a few instances where you can use HPC. If you have a lot of matrix computations, there's a lot of specialized hardware that excels in these matrix computations. MLAI is another area, as I've mentioned before, but also genomics or astronomy are other areas where HPC is used a lot. So that same survey that we did earlier, when we asked the same users, when they went from non-HPC to HPC, what kind of speed ups that they saw. So what we see from this chart is there's two bars. The blue is non-HPC and the orange is HPC. So for people whose code ran in under 1 hour on non-HPC resources, they saw about a 33% speed up. So even for these smaller cases, 33% speed up in their in the time it takes to run their code. And this is more user data, but we see the biggest savings here in this 1 day and 1 to 3 days and 3 to 5 days. So if I look at this 1 to 3 days, it takes about 1 to 3 days for you to finish just a single simulation. But then on an HPC, that same simulation, you get about an 80% speed up. So it runs much faster. You'll be able to get your data quicker. You'll have more time to analyze your data and actually do the science with that data. So this makes a case for switching from personal computers to a high performance computing cluster. Okay, so I've talked about this. There's potentially a case for anyone in the audience to move from their desktops to an HPC cluster. How would you go about doing this? So that's this next part of applying for an allocation. And here I want to bring up the large number of places where you can get HPC resources. So here we have both national, federally funded resources and private providers. You probably have heard of Google Cloud, Oracle, Microsoft Azure, or AWS, Amazon Web Services. All of these are private providers, but then also federally funded. There's the US Department of Energy, NASA has its own cluster. So if you're working with any of these agencies, it's a possibility that you can get an allocation on these from these federal agencies. The one that we'll focus on in this workshop is what is the NSF Access. So the National Science Foundation has this Access program, which has a number of resource providers under them. Open Science Grid, Pittsburgh Supercomputing Center, Indiana Jetstream, Texas Advanced Computing, and then UCSD's San Diego Supercomputing Center. So this box down here are the local resources that's available on campus. There's 3 of them. So going a little more in depth of those 3. And I've ordered this in terms of difficulty to obtain access to that cluster. So the simplest one is Expanse training account. You have to send an email and they'll, for this workshop, for instance, you just registered with your email and everyone should have received a training account and for you to be able to set up your own training account. So this is the fastest, but these training accounts are for limited duration, typically for a workshop like this one. There's the Research IT cluster. It's slightly larger scale, but also limited in what you can do overall. This quarter, it is our intent to give you access to a HPC cluster through what is called as the Campus Champion allocation. Beyond this, there's TSCC, the Triton Shared Computing Cluster, and you'll hear about TSCC in a little bit later today. And then there's SDSC's Expanse cluster, and you'll hear about this one as well. So, but beyond UCSD, we have all of these nationally available HPC resources. Almost all of them, or most of them, are funded by the National Science Foundation, and it's a collection of digital resources and services, including supercomputers, visualization, and storage systems. So one of the things we are encouraging here is for everyone to use NSF Access as a way to get an allocation for whatever research you are trying to do. So there are different levels, as you see on the screen. There's Explore, Discover, Accelerate, and Maximize. These levels might seem different if you're previously an Exceed user, but if not, that's fine. And you're not familiar with Exceed. It used to be called Exceed before, and now it's moved to Access. So this slide gives an overview of the first 2, which I think would be appropriate for first-time HPC users. So those were the Explore and the Discover levels. So in Explore, it is intended to be resource evaluation. This might be of interest to quite a few people here. Grad students are allowed to apply for an allocation. And you can do this on your own. You don't necessarily need to have an advisor apply for you and then you get added to your advisor's account. You can do this on your own. And the entry to barrier is very low. All you need is an overview, which means just about a half a page of what you intend to do with the allocation, what's your affiliation, in this case UCSD, and what your research topic is. So with just that bare minimum requirement, you'll be able to get access to this Explore allocation, which gives you 400,000 credits. And that's quite a bit. In a minute, I will say what these 400,000 credits actually translate into in terms of number of hours that you can run on a cluster. For slightly more research needs, you can move to the Discover. So this is modest resource needs, campus champions, large classes, things like that you can apply to the Discover level. Here you won't, a grad student cannot apply on their own. So usually a PI, so if you're working with an advisor, the advisor can apply for the grant. And once they have that allocation, the PI can add you to their allocation. So you will also have access to that allocation and all of the resources. So the NSF Access, Explore, and Discover are a great way for you to get started with HPC and get access to a lot of these high performance computing clusters. I briefly mentioned about campus champions in some previous slides. I want to give one slide focus on this. So campus champion is, it's nationally. A lot of universities have campus champions. I'm one of the campus champions at UCSD. There are others who are also on the call, Sid and Kim. So you can reach out to any one of us, and the intent is for us to be able to add you to our allocation. So if you have never used HPC before, you could send us an email and we will add you to our allocation and let you try out an HPC resource for a limited amount of time. The intent is for you to explore this HPC resource, see if it is the right fit for your needs. And if it is, then you can go and apply for your own allocation. So instead of you not knowing how to apply for an allocation initially, or not knowing if Expanse or any of these resources are right for you, you can come to us and explore HPC first through our allocation, and then apply for, and then once you have a feel for it, you can apply on your own. So this was when I first started exploring whether I can get an HPC allocation, it was a chicken and egg problem, because usually they will say, does your code scale well onto HPC resources? When I started, I didn't know if my code scales well onto HPC resources. And usually when you write a proposal, they ask you for that. So this becomes a chicken and egg. You need HPC resource to explore scaling, but to get that HPC resource, you need to show that you can do scaling. So to overcome this, this is one way to overcome that. We will add you to our allocation, try it out, see if your code runs well, see if you're able to do the scaling. So when you actually apply for your own allocation, it'll be easier. You can put all that data in there that says, I tried some basic scaling, my code works well on HPC resources, and it'll make a more compelling argument for when you apply for your own allocation and proposal. So one of the things that campus champions can do is what's highlighted here in bold. Through NSF Access, we'll have HPC allocation intended to allow researchers to quickly try out various resources, not just here at UCSD, but nationally. And at the end of this workshop, that's what we will be doing. I'll ask everyone to create an NSF Access ID, an account. And if you'd like, give that NSF Access ID to me. And then in the backend, we, myself, Sid, and Kim, we will add you to our allocation so that this entire quarter, you will have access to all of these different HPC resources and see which of these is appropriate for your needs. I see a question. Is the compute credit for Discover supposed to be 1.5 million or 150,000? Thank you. Thank you for that. That's a typo. It's 1.5 million. Okay, so going back to this here, there's 5 different ones that I've mentioned. The training account. The second one is a Research IT cluster. So I'll now talk about the Research IT cluster. It's a free service that's offered to all faculty, research staff, postdocs, graduate and undergraduate students. And it is intended to be another easy way to get access to some of these HPC resources without having to write a detailed proposal or apply for a detailed allocation. And Sid and Kim are part of Research IT, and it is a service that Sid has a comment that access allocations are distributed in half increments. Once half the allocation has been used, the other half is released. Thank you, Sid. So the UCSD Research IT is one possible avenue for you to get access to HPC resources. Another possible avenue is the Triton Shared Compute Cluster, TSCC. And I will hand it over to Yuhu, who will go through the next few slides and explain about the TSCC.
Thank you, Darshan. Thank you. So, hi everyone. This is Yu Chen from the TSCC User Services Group. So, TSCC is a supercomputer cluster managed at SDSC. We provide TSCC to the UCSD research community as well as other academic institutions or industries for them to do their research, their industrial works or any other HPC related works. So next slide, please. Okay, so TSCC provides two computing models. So we call it condo and hotel. So a condo program is for our users to purchase computing hardware, which we call compute nodes, and then join those hardware to the HPC cluster, to the TSCC HPC cluster. So by doing this, the condo users can not only have their access to their own hardware, but also a large, like hundreds of other compute nodes on the TSCC clusters. So the condo owners owns those hardware, and they can put their hardware to TSCC for 5 years, and after 5 years, the hardware is still owned by them, and they can choose to pitch the hardware back to their lab or let us to surplus of it. And the second program we have on TSCC is called the hotel program, so which is for the user to purchase some computing time. So we have a small portion of the HPC clusters accepting the hotel jobs and the tasks from the hotel users. Next slide, please. So the TSCC has been run up online since 2013, almost 10 years, and then now we are upgrading our TSCC architecture to the TSCC 2.0. We call it TSCC 2. So besides the computing hardware and computing time the users need to purchase, we are offering other hardware upgrades, such as what we can see on this figure. We are offering a new parallel file systems for both the Scratch and the home directory. We are offering new switch and a new operating system and the job schedulers, and all costs are on us, but still keep our users computing hardware on the cluster. We are trying to make our TSCC to better for our users' need without adding any extra cost on our users. So Next slide, please. Okay, TACC also provides free trial accounts, which has 250 core hours valid for 90 days, which is often enough for graduate students to complete a project. So if you want to request a trial account, you can email us and let us know your basic information, such as your name, email address, department, institution, affiliation, and please let us know what you want to do with TACC. And you can also find more information about TACC on our website, which is treatingcluster.sdsc.edu. And please let me know if you have any questions. And thank you. That's the introduction about TACC, and I'm going to give the talk back to Darshan.
Thank you, Yu. Do we have any, before moving on, any questions about TSCC? Okay. So everything that we have talked about so far is summarized on this slide here. So the good news is that there's 3 different places where a grad student can get a free account on campus. Grad student or an undergrad student. Research IT, you can submit, you can email them and get access to a research IT cluster. As you just mentioned, there's the TSCC. You can get a trial account, which is usually good, should work for a project. If you want more time, however, through the campus champions, you can submit a form, and I have this form, a QR for this form at the end of these slides. And within a week, you should have access to a lot of national resources, including SDSC's Expanse. TSCC, you can purchase time. Here your advisor would have to get involved of the condo model or the hotel model, and then an advisor would need to purchase time or nodes from TSCC. Other options are this access, explore, discover, accelerate, or maximize levels that I mentioned initially. And as the scale of your problems becomes larger, you'll have to move more and more towards this accelerate and maximize levels. But if you're starting out, it's your PhD thesis, potentially you don't need these accelerate or maximize, and you can use the explore and discover levels. Especially the explore level is great since a grad student can apply for it without an advisor. Okay. So any questions up to now? I've talked about you can try out HPC, and that's what this workshop is heavily focused on, just getting you everything you need to try out HPC. But then when you have to apply for an allocation on your own, I've presented quite a few different options that researchers on campus have to get an allocation. Any questions up to this point? Okay. Any questions on Zoom? So you have an allocation, and I've mentioned that SDSC Expanse is just one of the different HPC resources nationally. There was a chart with a lot of them. The next step is to take that allocation and use it to access one of these clusters. So here the question becomes, which resource provider is right for you? There's Expanse, there's Pittsburgh Supercomputing Center's Bridges, Texas Advanced Computing Center, TAC. There's a lot of these different resources, and here is a list of all of the different nationally available resources. So it's a lot then, and the question is, how do you pick the one that is right for you? So some of the things that you can consider is whether it's short-term or long-term project. Do you really need a graphical user interface? if some kind of visualization is necessary, the job length, number of codes, or the memory requirements. So based on some of these things, one resource might be more appropriate for you than the other. And over the next few slides, I'm hoping I can give some guidelines on how to go about making that decision. So here's one example here. Let's say you applied for NSF access and you got 400,000 credits. What can you do with those 400,000 credits? So there's a nice exchange calculator that NSF access gives you. And this will allow you to say 1,000 access credits gives you how much on a particular resource. Now, key thing here is that this is a GPU. GPUs are expensive. So 1,000 credits only becomes 19 credits on that particular GPU. And then how they, what does 19 credits means is different based on the resource provider. But roughly, broad generalization, but it can roughly be thought of as 19 hours, 19 core hours on that on that particular resource. So when you want to know how much your access credits are worth, this exchange calculator will give you a way to put in that number and let you know exactly how many hours of time you actually get on that particular HPC resource. So I'll go through bridges, and then there's Expanse, which Mary will talk about, and then I'll also talk about Indiana Jetstream. So these are the three which I'm most familiar with, but as I've mentioned, there's a very large number of them, so maybe some others are also appropriate. So one of the resources is Pittsburgh Supercomputing Center's Bridges 2. The key from my experience with Bridges, one of their key, the nice part is this one here. It gives you 4 terabytes of memory. So if you have a job that really requires a very large amount of memory, possibly Bridges is the right one for your application, just because it's 4 terabytes, and the other two, Expanse and Jetstream, don't go up to 4 terabytes. But there's a trade-off. It only has a V100 GPU. It doesn't have the more advanced A100s, or now NVIDIA's come out with H100. So those GPUs are not available currently in Bridges. The maximum runtime here is up to 5 days. So I will now switch over to a bit of a demo. For people on Zoom, do you see my browser? Excellent, thank you. So when you log into Bridges, you see here, this is saying Bridges on demand. This is what the interface looks like. They will, once you apply for an access allocation and they will add you to Bridges, they'll give you a username, and then you set your own password, you enter those details, and it'll come in here. It's quite convenient. There's a home directory that you can then go to. It'll give you all of the different, it's almost, yes. Yeah, thank you. So there's a home directory that you can go to, upload files, download files. So if you want to transfer things from your local machine to the cluster, this is one easy way of doing that. So that's the file system. And then, of course, there's a shell access. So once you click on that, it'll ask you for the password. And then once you have that, you now have a shell environment. It tells you which account that you have, the number of SUs. This is the credits that I was talking about earlier. And now here you can, it's a shell access, and you can use this, you can run your job, get an interactive node, things like that. So this was very briefly bridges. As I mentioned before, one of the key features there is if you have a very large job that you want to do, which requires up to 4 terabytes of memory, bridges might be the appropriate resource for you. It is different from Expanse. So could you repeat that question, please? Yes. So there's a question from the audience that once you have credits, can you use both Expanse and bridges? So the answer is you're given 400,000 credits. So let's say you applied for that first level and you were given 400,000 credits. You can request time on any of these resources. So you're not automatically given all of them. You saw that there was a very large number of those. So you're not given access to all of those. You can request time on Expanse, you can request time on bridges, request time on any of these. Yes.
Has to be approved by the and it can take some time to set that up. So it won't happen overnight. Keep that in mind. You can't use whatever you want. You can close one down and move to another machine, but it can take some time. Would you repeat that?
Yes. Yeah. Thank you, Mary. So one of the comments was that it can take time. So yes, you can move from bridges to Expanse to any of these other resources, but every time you do this, there has to be a request that is sent, and in the back end, the support team at each of these different resource providers, they have to make that transition. So it can take a couple of days. It won't happen immediately. Yeah. There's another question. Okay. So another question from the audience here is, do all of the different nodes share the same memory? And can you, so the answer there is how many cores are there? And then do they all share the same memory? Depends on each resource. So I can't give a more specific answer. So at the bottom here, there's this for bridges, there's this user guide. So if you go there, it'll tell you how many cores are available per node. More generally, a single node, every core on that node shares memory. But when you have multiple nodes, they don't by default share memory. So you will have to write specific code that allows you to parallelize across multiple nodes. But if you're restricting to a single node, they will all share memory. Maybe you know that. Yes. One comment in the chat: most systems only have shared memory within a single node. So all the cores within that node would share a memory. Thank you, Marty. So this everything that I showed on the live part. Oh.
Question is, what is the allocation Expanse provide for a single user? Is it depending on our request?
What is the allocation Expanse provides to a single user?
Does it depend on our request?
Maybe you could unmute yourself, and I'm not sure I understand the question. or if you could provide more details in the chat.
So the thing is, like, what I'm asking is, like, for every single user without after this NSF application, like how much allocation time or the hours or the notes each user will be provided for their users?
Thank you. Okay. So depending on the type of allocation that you apply to, so let's say the allocation that you apply to is the Discover access. So now you have 1.5 million NSF access credits. These are access credits. This is not time on any particular machine, or like Expanse or Bridges or any of these.
I see.
So now you will exchange those credits for time on any one of this large list of nationally available HPC resources, and how much time you get on them is dependent on this exchange calculator. So once you have the allocation and you have your access credits, you can go to this exchange calculator and calculate the time you get on that particular resource. Does that answer the question?
Yes, thank you.
Thank you. Okay, so everything that I showed in the live demo is also on the slides, and the slides will be shared with all the participants. So this is here for completeness. Next is Expanse. So Mary will take over and talk about Expanse.
So while he's setting that up, so I've been working on putting together training materials and training programs with our HPC training people and user support people and experts for teaching people how to use Expanse and do HPC systems. So I'm going to give you a really quick overview of Expanse. That's a picture of it, and we might be able to do a tour of the data center next week if we have time. And it's really fun to go in and see what these systems look like. The data center has several rooms bigger than this space we're in. It's hot, it's noisy, it's windy, and you really get an idea of what these systems sound like. This is a picture of Expanse, and you can see it's all lit up. They have liquid cooling now that everybody's proud of, and this is called a rack, and I'll talk about these racks. They're called scalable compute units. It's an innovative design concept by the Expanse team that's being emulated now on other systems. So I'll go into that in more detail, but it does help to know if you don't know what a computer rack is. That's this big tall thing. We plug hardware into it, servers and storage and all kinds of things like that. They have to be connected with cables. And then because it does get hot, they use these days liquid cooling. So that's what Expanse looks like. This is what Expanse is about. And without going into too much detail, Expanse was designed for what we call the long tail of science. And this is a concept SDSC came up with quite a few years ago before we got the Comet system built. And the idea is that, yes, there are these applications and models that need to run on a million cores and go to exascale and zettascale, but most of us are not at that level of need. We're doing what's called average, only a few thousand cores you might need if your model even scales that high, or you may be doing AI machine learning where you're moving a lot of data in and out really quickly, so you need an advanced network, but you don't need exascale computing. And those are big systems. Like at Oak Ridge, they have a system where there's 100 racks in a room, bigger than this, and they have to synchronize 100 racks with all the node hardware on it to do exascale. So what's the more usual? What they did was they looked at the average size of a job being run on Exceed machines and high-end resources at that time, and came up with a design to meet the needs of those people. So if you think of a Gaussian distribution, the peak as far as what kind of flops they need for operations is in the middle. Most of the jobs are down in what we call the long tail. So that's what this is designed for. So you can get a quicker turnaround on your smaller job. And I'll go into a little more detail about that. So that's what long tail of science means. And although, astronomy, genomics, earth science, social science, and other sciences run on it, but it's probably best for these kinds of applications. And Darshan, for example, will talk to you about your application and what you might really need. It might not belong on Expanse. There are other systems that excel in other science domains. So we don't take it personally. We want you to run on the system where you get the most results. So we have, at the moment, 13 official scalable compute units, but they keep adding more owned by industries. So it's growing slowly, a little bit at a time. It has 728 compute nodes on. So these SCCUs, that's one of those racks that I showed you. And then mounted into those racks, I don't know your background. I'm going to assume some of you build your own clusters and some of you have never seen one. You're just running jobs on these systems. So the nodes they slide into these racks, and we have regular compute CPU nodes and also GPU nodes, the NVIDIA V100 in particular. So those are called accelerators for making your job run faster, like you might call them from a main application. And then we have some what we call large memory nodes with 2 petabytes. Other systems have 4 and 8 petabyte nodes. It just depends on the system you're looking at. If your job is extremely data intensive and you need 4 petabytes on a node, well then you would go to a different system. So it all depends on what your requirements are. You asked about how many cores are on each node, right? Is your job core compute intensive? Is it memory intensive? The cores will share memory on a node, so like on our system, and I'll go into that. It just depends on your application and what you're trying to do. And part of the challenge of HPC is A, getting on the system, and B, making your job run well on the architecture you're working with. And then Expanse also has innovative ideas for what we call composable systems, which is edge computing, high throughput computing, gateways. We have 1 million users on our gateways. And a science gateway, I won't talk a lot about that. That is a web portal where you have a model or an application with a huge community that uses it. They don't all need to log on in some cases. They can go through a portal and you have some team that installs your application in the back end, and you have these a large community of users then that just run jobs through the gateway, and they're really happy. They don't want to develop the model. They just want to analyze their data. So that's a gateway. And then container computing, interactive computing, I'll talk briefly about that, and cloud bursting. We have a lot of data. I'll just show you the architecture diagram briefly. 12 petabytes of high performance storage, 140 gigabit per second, fast IO nodes, Ceph object storage, and high performance networking all through. So again, to repeat the message, Expanse is, and I see a lot of questions, and Marty Candace is an expert in our user support group. He's there to answer any questions. Feel free to ask away, and we'll do our best and answer what questions you have. So again, it's built by Dell. They're called the system integrator. They take all the hardware and they literally build one of those racks, and we get a big wooden box, and in it is the assembled rack. But that's their job, is to figure out the interconnection networks between the racks, and there's several companies that do that. Dell did ours, and it's at, right now we're 5.16 petaflops with the 13 scalable compute units. And again, I'll show you a little more detail on that. The core principle is the majority of computational research is performed at what we nowadays call modest scale, only 1,000 or 10,000 cores kind of thing. That's still pretty big compared to even 10 years ago. So everything grows with, computer programming and science. You'll take whatever is available and expand to use it. There are limitations, like the jobs will mostly run less than 48 hours. If you need more, you can work with our team, and the team will arrange a special condition. But again, modest scale computing, jobs that would get done in a couple of days are what we support without any question, but we can do special circumstances. And then we're part of the NSF Advanced Cyber Infrastructure Coordination Ecosystem Services and Support, the Access Program. Darshan gave you a little bit of an overview of that. It's a big site. It's evolving. It's only about a year old. It's very a new way for NSF to approach their cyber infrastructure ecosystem. And if you don't know what cyber infrastructure means, tell me when I have like 5 minutes. If you don't know what cyber infrastructure is, it's a term coined by NSF to aggregate this ecosystem, is a good word for it, but to aggregate the high performance computing clusters, the networks that you need to interconnect them, the data, the places where you need to store your data, the networks to move your data onto those high performance computing systems, the software, the security. It's an awful lot of moving parts that are part of the national computational infrastructure. And so they put it all under one umbrella, because that's a lot of words for me to say every time I'm talking to you about the resources and services. How many times I typed all that out in papers and proposals. Now I can just say cyber infrastructure. It's not a common term, it's becoming more common. The Department of Energy, for example, doesn't use it yet, but they're learning that it's a good term. So anyway, we're part of that whole ecosystem. Before Access was Exceed, XSEDE, and it was the same thing, only everything was organized in this monolithic group, and everybody registered and had information associated with them. With the Access, it's really more like we have a portal, and beyond that, it's a little more decoupled. They're trying to decouple that so things grow organically, and a lot of communities can get support and participate. And participating is really important. All right, so there's the architecture of Expanse, showing these different compute racks. And this is so far away I can't read it here, but the summary of the resources that I showed you in the summary diagram on the left, it just sort of summarizes what's in it. Each one of these black vertical boxes is a rack. And in the rack, you have things mounted. Those are called servers often, or data storage. And on those, so on each rack, the idea is most of our jobs are going to fit on one rack. If you just need to run stuff on one rack, it'll be much more efficient for you. Get your data on, job runs, communication is local, everything runs faster. So that's one of the ideas behind these racks. So you have CPU and GPU. We're assuming acceleration is going to become more and more a part of future computational work. And again, we've got these 13 racks. And then they're interconnected with very high-speed networks. I jokingly tell people, if you like the way networks work, that is just an amazing field of how do you interconnect, 13 racks with 728 nodes so that they all have about the same communication time. That's the goal. And they do it. They actually get there, but it's very complicated. There's a lot of design that goes into the interconnection network switching algorithms. And it's the same out on the network, out on the internet. Your signals go out on the internet somewhere. You use this every day. And how do you get a signal from here to a server in New York and some data you're pulling from Washington, and it's got to go down into Texas or something like that? Those interconnection switches are just as complicated. They're just a little bit different. So we've got these highly intelligently interconnected scalable compute units, and then we have high performance storage. The Lustre file system is one of them, and you'll have access to that. It's just a few, petabytes. But a lot of people have to move their data off and on the nodes, and then they store it on these petabytes of data. So you could take advantage of that. Any questions that I need to have? Marty looks like he's taking care of that. Again, re-summarizing the system. So scalable compute unit details. And why am I going into all this detail? Is it helps for you as a non-systems designer to have some idea of how complicated these systems are. So when you have problems, you won't feel bad about asking a question. It really is, you'll have something that's running every day, and then one day it doesn't run. And any one of these 1,000 things between you and your job running and your answer can go down. And so the idea is, if you have some understanding, you at least appreciate how complicated it is, so you can ask questions from people like myself and Marty. And so each of these compute nodes has 2 AMD EPYC Milan, from the Milan family, CPUs, and then they have 4 NVIDIA V100 GPU nodes on them as well. And so you can, each of these Milan CPUs has 128, well, the node has 128 cores. So you ask that question about the core. And then it comes down to how many cores, like the newest Genoa version has 96 cores, but it's got a lot more memory. And so the memory access is often what slows you down, moving things in and out of the local and remote L1, L2, L3 caches. There's all these concepts that you end up, when you start optimizing your code, you worry about. So I won't do a lot of discussion about that, but it's a very unusual processor architecture. So you basically have these 8 core CCDs on the EPYC node, and they have their own local memory, and then they share memory across the node with each other. All of these are designed to help things run faster. We have DDR4 memory. A lot of these things may or may not mean a lot to you guys, but the idea is that you have to kind of, depending on your application, you want to be aware of the fact that these cores are arranged in a particular physical arrangement with each other, and then with the other cores on the node. And that can, if you have something that is memory intensive, for example, this might affect how you might structure how you're moving your computation around. It's just a little, normally you might not even notice it, but I do know of some memory intensive applications that they need to be structured to run better on these. They'll run, but you might want to make it run better, more efficiently. And then our connectivity fabric, we have a really high speed network. If it's, for us we talk 100 gigabit per second with the expectation that that's what we're going to be getting on our system. So a little bit better than the 10 megabit maybe or 200 that you get from Spectrum to your house. But when you log on to a terminal, and you'll learn about that this week and next week, when you log on to a node, you're now inside this computer system. You're not working at home. You'll be working internally with the speeds of that system. Okay, so finally, I think this is, we have the Expanse user portal. And next week, hopefully at the end of our interactive session, you'll have a chance to work on that. The portal is great. It's a web interface to the Expanse computer. I don't know if anybody has asked for a raise of hands. How many of you know what Unix is and have worked on a workstation through a terminal? Right. So this is the hardest part for new people coming onto a system like Expanse, and the pain point of having to grow your research into and putting it onto a supercomputer. It's the operating environment, the user environment. It's not very warm and fuzzy, but portals, they do help. We have MATLAB built into there. We have R, we have Jupyter notebooks. So if you have a notebook, you could just plug that in and get it running. Yeah, we have a question. I don't know if we even have, Marty, do we have parallel, do we have Mathematica running on Expanse? That I think it's on TSCC. You?
Yes. What?
Do we have Mathematica running on TSCC?
Mathematica? Yes, we have. I thought we also have it on Expanse, no?
I don't know. I'm asking Marty. We have MATLAB, but I don't know about
Yeah, I'm not aware of anyone running Mathematica. I don't really know what the licensing is for that. I know we don't have a site license, so I don't know if like a personal Mathematica license would allow you to run it on Expanse or TSCC. We could check on that. I know the university has a sort of university-wide license, so it might.
Oh, I mean, so nobody's asked. Oh, sorry, Marty, go ahead and finish.
No, yeah, I mean, I haven't really explored the parallel options in Mathematica myself before. I mean, it's more symbolic computing, but yeah, it might be possible.
it would be interesting, and like Marty said, we'll show you next week. You can send a note to consult@sdsc.edu, and you get really nice people like you and Marty answering questions. And so you can, if you're, after next week, we can talk, and if it's something that you'd really like to see, and it would advance your work, we can look at where you might best need to be located. The TSCC is great, but it's a hotel condo, and you have to have ownership in it. And you can talk with us next week about that as well. You're asking me, is this portal like a virtual machine in the sense of Jupyter Hub? You can get the software that we modified to develop the user portal. It's made by a group at Ohio State University called Open on Demand. You can install it, but that doesn't mean you can connect to Expanse very easily and very readily. You'd have to modify the heck out of it. So if you're looking for ways to access Expanse remotely, next week we'll talk about Galileo, which is a Jupyter notebook project that we've been developing, and Marty maintains this amazing version of you run Galileo on a node, and up comes a secure Jupyter notebook. So we can talk about what you need to do and get a little more customized idea. Cindy?
My confidence that it has a Jupyter Hub-like capability.
Do you know what Jupyter Hub is? Okay. Okay. Okay, all right. Okay, well, we can talk with you more about that. Darshan can, looks like we have some specific needs for this guy. Yes.
Always been negative kind of. The second thing is I have to worry about the license.
Marty would be able to answer A. B, you don't worry about the license. If we have it on Expanse and you're a user, you're part of our license. And so Marty, his question was, he uses MATLAB, and does he have to worry about a license? And is it always the most current version?
I mean, we stay pretty regular with the versions, but if there's a new one out, we just haven't put it on the system, we can always do that. Yeah, MATLAB, there's like a site-wide license for UCSD, so yeah, that's not a problem. Anyone on Expanse can use MATLAB. You know, depending on certain software, there might be restricted licenses.
We'll go through how to use Expanse with my Expanse 101. Thanks, Marty. And my Expanse 101 material. And part of it is looking at something called modules, where you customize your environment. Let's say you have some stuff that runs with MATLAB 1.2, and I forget all the versioning. And you've got new stuff that's MATLAB 1.4. And they've got both of those installed. You build one environment for MATLAB 1.2, and then you change out and you build another environment. And you can dynamically change your environment. It's a little messy at the beginning as you learn how to keep all the balls and strings together. But once you figure it out and you develop it, you have a formula for each, a customized worker environment, user environment for each application. It's really lovely. So we can also, Darshan can help you figure out. And if you need something and you have a valid need, then our user support group will do their best if it's at all possible. But it takes a little while to figure out, you know, how to deploy a particular version of software. Apologize, the planes are flying over. It's not too bad, but it might take a while to figure out how to get it onto all 758 nodes. So you have to have a little bit of patience. And that's the end of my talk, and we'll do more actually hands-on stuff with Expanse next week. Okay, thank you.
Okay, so far we have looked at two national resources. We looked at bridges, and Mary talked about UCSD and SDSC's Expanse cluster. The last one that I'll be covering here is Indiana Jetstream. So here are some of the specifications. So you'll see that on here it's only 1 terabyte, whereas Expanse had 2 terabytes, Bridges had 4 terabytes. But the GPU nodes are A100 here, whereas both Expanse and Bridges were the V100. So if your application really needs a more advanced NVIDIA A100, which is the generation after the V100, then perhaps Jetstream is the resource, that is the HPC cluster that you would want to run your application on. The other feature of Jetstream is what they term always on infrastructure. And I'll switch to the browser to show that one. So this is the Jetstream login page, and then once you log in, see if this works or if it'll ask me to log in again. Okay. So once you log in, you will see your allocation. So this is the allocation number that I have. And then you have these different instances that you can create. So one of the nice things about Jetstream is I created one instance called Workshop. And here it lets me launch a web desktop. So this is now almost like a Windows or a Mac, but this is Ubuntu in this case. But if you are very uncomfortable with the shell or just terminal access, and you would like to do things in a graphical user interface, then Jetstream may be one way to get. It's a lower barrier if you don't have access to that. There was a question about MATLAB, and I haven't tried Mathematica here, but with MATLAB, it's installed on Jetstream, and you would have access to this GUI-based MATLAB interface. So Jetstream may be one option for some users who either need a A100 node or they're more comfortable with this graphical user interface. Oh, and there's a comment by Yuvu that TSCC has Mathematica 13.1.0 installed system-wide. And user support staff Jerry has the license and knows to install it on Expanse and TSCC. So for Mathematica, should be able to get that. So these are just some slides that go through the live demo that I did. So these were the three that we covered: Bridges, Expanse, and then Jetstream. And almost all three of these have access to all these different, excuse me, all these three different softwares. And these are the most common ones that a large user base, a large number of users try to run their applications on: these MATLAB, Python, Anaconda, Jupyter, or at the bottom you see PyTorch and TensorFlow for machine learning and AI. So there's a lot of information that we covered here, and we've only looked at these three. But as a reminder, we have a lot more. That's all of these. So the question might be, how would I even go about trying to pick among all of these and see which one is right for the science and research that I'm doing? One potential option is what's called as this XDMod tool. The website for that is here. And I will briefly touch on XDMod here. So this is the dashboard of XTMod, and it lets you, and you can log in with your NSF Access account. And it gives you a lot of information about what other users, what other people are doing. So for example, I go to this usage explorer, and I look at these total number of node hours by field of science. And this is, I pulled the data for UCSD. So you see here that so materials engineering is the highest, and there's astronomy, biology here, fluid and plasma physics. And what's even more nice is you can click on any of this and then go to, for example, the resource. And in this case, you see that a lot of materials engineering researchers are running on Expanse. So there's a higher likelihood that a lot of your domain specific tools for materials engineering might be installed on Expanse, so there's more documentation available for that on Expanse. Whereas maybe some other field, so instead, if I look at, for example, astronomy and planetary sciences, here the users are more gravitating towards bridges to for their science. So it could be the case that domain-specific tools for astronomy are on bridges. Just another way for when there's so much information available, how do you pick the resource that you would like to use? This XTMod is one possible way to filter by the field of science and see which of these national resources are being used. Of course, there's a lot of other factors like I mentioned, the size of your job, the time that you need, the amount of memory, which GPU that you would like to use, etc. So that's XTMod, and this is a slide that just shows everything that I clicked through in the browser. Okay. So finally, we have talked about all these different things. Now let's actually get everyone access to NSF Access. I'm using Access as an overload here. So this hands-on part of the workshop today, if you would like to try any of these resources and want an account and being able to access any of these clusters, please go to this website and see if that shows up. I will put this link in the chat. What is this? So the link is in the chat. So the most for everyone who's at UCSD, the most common way to do this would be this one here: register with an existing identity, and you can use your university SSO, so it'll direct you to the AD directory, the login, and you'll be able to access it from there. So if you have any trouble with that, please let us know. So now it'll all this is the hands-on part. So we'll wait for everyone to have completed this step before moving to the next one. When you click on that register with an existing identity, it should take you to a page that lets you select the identity provider, and from the drop-down list, you can pick UCSD. And then when you hit log on, it'll direct you to the AD login page. Once you have completed this step, if you could put in the chat that you have completed, just to keep track of who all have completed and if anyone is having trouble. Thank you. If you have completed this step, you'll likely get an email with your NSF access ID. My case, it is my first name and my last name, so D Sarojini. Probably a similar. And if you have completed that step and you have the access ID, then please fill out this form. It just asks you for the first name, last name, and in particular down here we see the NSF access ID that you got from when you registered on NSF Access. And we'll be using this form to later tonight and over the next 2-3 days, adding everyone to our Campus Champion allocation. And from that, we will then add you to Expanse. So that whole process might take some time, but you have the training account in the meantime to do the next week's training. And beyond that, you will have access to Expanse through this Campus Champion allocation. So everything so far is focused on just getting everyone who's part of this workshop access to a cluster, first with the training account and then through this Campus Champion allocation. But the intent is for you to try out the HPC cluster, find the one that best fits your needs. So you can try Expanse, Bridges, or any of the other clusters that are available. But the intent is once you have that, we'll give access for 90 days till the end of this quarter. And if you'd still like larger resource allocations, or you want to continue your research on any of these clusters, you can then submit your own proposals to any of these 4 different levels that are available to you, and then get your own allocation and then continue your research with your own allocations. And as a reminder, grad students can apply for allocations for your thesis using the Explore Access level. So just a quick wrap up and what we will be doing in day 2. That's next week. So everyone has an Expanse training account. We'll be following some of the tutorials that Mary and her team have put together. It's an Expanse 101 tutorial, and then learn to launch a secure Jupyter notebook on Expanse, and then using the Expanse portal, which also Mary briefly touched upon in her presentation. And if you'd like to do more advanced things, we will point you to tutorials that are available to you. So that's the end of day 1. Anyone who, if you have any questions, struggling to get the NSF access account or filling out the Google form, please stay back and we'll try to work that out. Thank you for attending, everyone, and see you next week.